Hey everyone, today we're diving into one of the most beautiful ideas in all of physics, the deep connection between energy, momentum, and mass. And we're going to do it using this incredible geometric tool, an idea pulled straight from Chapter 8 of the book Newton and Relativity by Sester, Clemente, and Korf. It's going to be good. Let's get into it.
So if you've ever tried to read about special relativity, you've probably run into something that looks like this, the Lorentz factor. And yeah, it's a lot. It's mathematically perfect, of course, but for most people, it's just a wall of symbols. It kind of hides the simple, elegant truth that it's trying to describe. Which leads to the big question, right? Is there a better way, a more intuitive way to actually see what's going on with energy, momentum, and mass? What if we could just get rid of all the complicated algebra and replace it with a simple shape? Well, it turns out the answer is a huge yes.
So here's how we're going to do it. First, we'll start with a little geometric puzzle. Then we'll turn that puzzle into real physics. We'll explore the anatomy of this new tool we've built, and then we'll push it to its absolute limits. And finally, we'll see how, in Einstein's universe, geometry really is physics.
All right, first up, a geometric puzzle. Believe it or not, the key to unlocking one of relativity's deepest secrets is actually hiding in some math you probably learned back in middle school.
And here's the secret. That really messy-looking square root thing from the Lorentz factor, it's just one side of a simple right-angled triangle. Yeah, really. If you set the longest side, the hypotenuse, to 1, and the base to an object's velocity compared to the speed of light, then the Pythagorean theorem says the vertical side has to be that complicated term. The big secret was a triangle the whole time. Okay, so that's cool. They have this pure geometric shape. But what does that have to do with the real physical universe? Well, let's find out. Time for our next step, from theorem to physics.
This is the magic step. We take our simple little triangle, which has no units, and we multiply every single side by mc squared, a body's total energy. And boom, just like that, a pure mathematical idea scales up and transforms into a working model of physical reality. We've just created the relativistic EPM triangle.
So now that we've actually built this thing, let's figure out how to use it. Welcome to Section 3, the anatomy of the triangle. Let's take a look at what each piece of this puzzle really means.
This is where it all clicks into place. The hypotenuse, the long side, now represents the object's total energy, which we call E. The vertical side, that's its rest energy, the energy it has just by existing. And that bottom, horizontal side, that's the object's momentum. All three of these crucial physical quantities lock together in a perfect geometric relationship. But wait, you might be asking, where's kinetic energy? You know, the energy of motion? Well, this is what's so elegant. It's not a side of the triangle. Kinetic energy is simply the difference in length between the total energy hypotenuse and the rest energy side. So as an object speeds up and gets more momentum, the hypotenuse gets longer. And that gap, the kinetic energy, gets bigger and bigger.
And of course, because all these properties form a right-angled triangle, we can describe them using the Pythagorean theorem. You've probably seen this famous equation. E squared equals PC squared plus m naught c squared. It looks so complicated, but it isn't some weird abstract rule. It is literally just a squared plus b squared equals c squared applied to our triangle. We can now connect energy and momentum directly without ever needing to worry about velocity.
Okay, now for the really fun part. Let's see what this triangle can show us when we push things to their logical extremes. Let's jump into Section 4, Physics at the Limits.
First off, what happens when an object is standing still? Well, its momentum, the horizontal side of our triangle, shrinks all the way down to 0. The triangle completely collapses into a single vertical line. And look what happens. The hypotenuse, total energy, is now lying perfectly on top of the vertical side, rest energy. The picture itself proves that for a stationary object, total energy is rest energy. There it is, E equals m naught c squared, staring us right in the face.
Now let's try the other extreme. What if a particle has no mass at all? If its rest mass is 0, then the vertical side of our triangle, the rest energy, just vanishes. It's gone. The triangle flattens down into a horizontal line. Now the geometry says the total energy can't be 0 because that would break everything. So something really interesting must be going on here.
And it is. The geometry gives us no other choice. With that vertical side gone, the horizontal side, momentum, must be exactly equal to the hypotenuse, total energy. If you write that out, it means MVC equals MC squared. Do a tiny bit of algebra,
and you're left with one single inevitable conclusion: V equals C. The geometry itself forces any massless particle to travel at the speed of light. It's not a suggestion, it's a geometric law.
And this is not just some theoretical game. These are real things. The fundamental messengers of our universe. Photons carrying light, gravitons carrying gravity, gluons holding atoms together. These are all real-world particles that exist in this massless state, forever racing across the cosmos at the ultimate speed limit.
So, let's bring this all together and land the plane. Welcome to our final section, Geometry is Physics.
So this really sums it all up. A particle at rest is a vertical line. A particle with mass that's moving is a complete triangle. And a massless particle is a horizontal line. Every fundamental state of being is perfectly captured by a simple change in this triangle shape. It's that clean.
So in the end, this EMP triangle isn't just some clever mnemonic device or a trick to help you remember an equation. It's a blueprint. It's a visual representation of the universe's most basic rules. And it shows us that on the deepest level, the laws of physics aren't just described by geometry. The laws of physics are the laws of geometry.
And that kind of leaves us with one last thing to think about. If a truth as deep and as world-changing as relativity can be perfectly captured in a simple high school triangle, it really makes you wonder, doesn't it? What other huge secrets of the universe are just sitting out there, hidden in plain sight, just waiting for us to find the right way to look? Thanks for joining me.